Well, we can generalize what we have been doing for a 2 degree of freedom spring mass system to a system with n degrees of freedom. The assumptions that we are going to make is that we're working with lumped masses, not distributed masses. Well, in the next section about systems with distributed mass, well, we'll see that those systems have an infinite number of degrees of freedom. And we assume that these lumped masses are linked by springs and dampers, that the stiffness is proportional to displacement, that the damping is proportional to velocity, and of course that the system is linear. And what you can do then is write it as a second order matrix equation. This is exactly the same equation that we had for the 2 degree of freedom spring mass system, except now that of course these matrices here, M, C and K, the mass matrix, the damping matrix and the stiffness matrix, will be n times n. Okay, and this is here a vector containing all the forces acting on the individual masses. Okay, if you do the same trick that we had done for the 2 degree of freedom system, you end up with an eigenvalue problem. That is this one. Okay, we can write it slightly differently. M inverse K minus lambda I V is equal to 0. So this is our A matrix. So we can compute the eigenvalues, the eigenvectors, and we know that the natural frequencies are related to the eigenvalues. Okay, they will actually be the square root of the eigenvalues, which are real. And we also can compute the mode shapes. Okay, and these are related to the eigenvectors. Okay, so we can pursue. Remember that we have the matrix A, which is M minus 1 times K, and you can compute the lambda I and the VI, the eigenvalues and the eigenvectors. These eigenvectors you can stack into a matrix which we'll call the eigenvector matrix. That's how we called it in the linear algebra course, but in this course maybe it's a better idea to call it the modal matrix, right? And this modal matrix we can use to do a change of coordinates. So we can take our equation m y double dot plus c y dot plus ky is equal to f, and if we inject that in here and we pre-multiply by v transpose, this is the equation that we're going to obtain, and you can rewrite this as this equation here, where this one is diagonal. It's the modal mass matrix. This will be called the modal damping, and this is the modal stiffness. Okay, well, this one becomes diagonal. It was already diagonal, and these two, they become diagonal simply because you have diagonalized the system. It's kind of obvious for this one, but it's kind of new for this matrix here, because in the case of 2 degrees of freedom we had left out all damping. Okay, but you can show that under special conditions, I don't want to go too much into details, but also this new matrix for damping, modal damping matrix, becomes diagonal. Well, these are the equations that we had obtained. Okay, and all matrices here, this one, this one, and this one, are diagonal. This means that we have produced a set of decoupled first order differential equations. Okay, we can rewrite this by since this is a diagonal matrix, we can divide by the inverse, or sorry, pre-multiply by the inverse of this diagonal matrix, and we'll have this form. And this is the form that we had obtained for the 2 degree of freedom mass, except that we did not have this term over here. And doing that, well, in this matrix here, okay, which will be V transposed minus 1k V, well, this is our diagonal matrix with the eigenvalues. Well, you have here the natural frequencies appearing, and you can show that in this matrix here, which is also diagonal, well, you have here the natural frequency and the associated damping ratio. Well, we have rewritten a system of coupled differential equations to a set of decoupled differential equations. For each of these differential equations, we can find the solution, and it will always be a constant times a sign with the natural frequency times the vector t plus vi. So for each, and this you have for equals 1 to n, right? If you this is xi, so if you stack them in a vector, this is what you obtain, and we'll call this vector x. So we know that the solution of the original system, the general solution, it's our modal matrix times this vector x. So by finding the solution of these individual differential equations, we can find the general solution of the coupled system. Okay, the modal shapes are given by the eigenfrequencies and the eigenvectors. Well, we can solve now a very complicated n degree of freedom system. Okay, it's, you know that it's very easy to write this equation. Okay, you know, for instance, this one, well, on the diagonal elements you have to take the mass and look at all the springs that are connected to this mass, and on the off diagonal elements, well, you have to look at the, for instance, if you take element ij, well, you have to look for the springs that are connecting mass I to mass j. So it's very easy to construct this differential equation. We have seen previously that it's also a simple eigenvalue eigenvector problem to transform the system to a set of decoupled differential equations. So you can view that as n individual single mass spring systems. Okay, so you can find the solution x1, x2 and xn, and then simply you have the solution of the original problem by taking your modal matrix, okay, which we call V, okay, and pre-multiply the solutions that you had obtained from your individual spring mass systems. Well, we arrive here at our conclusions. Well, an n degree of freedom system has n independent degrees of freedom that you can use to describe the system. There is one natural frequency for each of the degrees of freedom in the system description, and there is a natural frequency Okay, and each natural frequency has a displacement configuration called a modal shape. We have done that for the 2 degree of freedom system. There were two modal shapes. One modal shape where x1, or it was y1, I think, y1 and y2 were moving in phase, and another modal shape where y1 and y2 were moving in phase opposition. Okay, so that's a modal shape, and we'll see in the application examples in section 5 other examples of a modal shape. Eigenvalues and eigenvectors are used to describe the system characteristics, and they are linked to the natural frequencies and the modal shapes. Okay, so this complex resulting motion, okay, can be decomposed in a set of equivalent 1 degree of freedom systems. Well, we know that the applied force or displacement excitation, it depends on the type of problem that you have, can be harmonic, periodic, or random. If it's harmonic, it's simple. If you look at the spectrum, it's just one spectral line. If it's periodic, well, you have a spectral line corresponding to the fundamental frequency, and then you have the harmonics. If it's random in nature, well, you have a whole frequency range. Remember also that if the system is linear, the response of the system will be in the same frequency range as the input excitation. So very often we have a complex system, but we know that our input contains only a few frequencies. So sometimes we are interested in an approximated model which only contains the excited mode. So for instance, let's draw here the frequency axis, and suppose our system has natural frequencies at these frequencies, okay, and that our input signal, okay, contains frequencies at this frequency, it's harmonic and another harmonic, and then you don't have anything else. Well, you see that you could construct an approximated model which approximates the behavior of the system around these 3 natural frequencies. So we have here a 5 degree of freedom spring mass system, and we count 5 natural frequencies. So this system can be, remember, be described by the following equation that you should know by now, is equal to F. You know that you can rewrite this by considering an eigenvalue eigenvector problem of this matrix. You can stack then the vectors in this matrix that we call the modal matrix, and it's V1 up to V5 in this case. So in this case here, M, for instance, has the dimension 5 times 5, right? So now if you use the change of coordinates Vx and you go through the math, you can describe it as x double dot plus cmx dot plus kmx is equal to F, and these are decoupled. Okay, so you can look at 5 different mass spring systems, and you can find the solutions x1, x2, x3, x4 and x5 and stack them in a vector, which we'll call x bold here, and you can then reconstruct the solution of the original problem by simply taking this modal matrix, and V times the vector x gives you the solution of the original problem. So now suppose that our excitation here is limited to 10 radians per second. Okay, so we know that we are never going to excite the modes or the eigenfrequencies that are related to this element and this element. Okay, so we can then use a simpler 3-degree of freedom model to approximate this 5-degree of freedom system, right? So how are we going to do that? Well, we know that this one and this one are not going to give you a contribution. So we can write that down as x1, x4, x5. Okay, so here we have v1, v2, v4 and v5. And what we do, since we are not using this element here, we cross out this column and we cross out this column. We have now a matrix V, which is 5 times 3, and we can approximate y1 to 1 y5. Okay, so we can use a 3-degree of freedom model, but we can still have the displacement of our 5 masses in the original problem. Well, many structures are free or unrestrained, and this means that they are not attached to a base, and a good example of that is a deep space structure, for instance the deep space telescope. If you do modal analysis for these structures, you'll see that you have a 0 natural frequency popping up. So one of the natural frequencies will be 0, and the corresponding natural mode, okay, is one without flexible deformation. It's called the rigid body mode. So this implies that the 0 frequency harmonic excitation causes a rigid body movement without deformation. This is sometimes ignored, but this should not be ignored by control engineers, and I think we are control engineers, because it's of crucial importance if you want to move the structure or you want that structure to track a given set point. Well, let's take an example to illustrate that. So here we have an unrestrained mass spring system. You see that all masses are free to move and they are not attached to some kind of support. We are going to use 3 masses that are identical, and the interconnecting springs and dampers are also equal. Well, the value of the damper is not so important because we are going to do a modal analysis. Okay, we have values for M and for K. It's pretty easy to obtain the mass matrix, which is of course diagonal. Here you've got it, and maybe we can do the exercise again to construct the stiffness matrix. Here, mass, the first mass, okay, element 1 1, there is only one spring connected, so it's K, whereas the second mass here, this is second element of the diagonal, you have 2 springs connected, so it's 2 times K, and then again the last mass, there is only 1 spring connected. The off-diagonal elements, well, 1 2, you look at the elements 1 2 here, and you look at the connecting spring, you put a minus sign, and of course you'll have the same thing for the element 2 1. Okay, this is telling you that this matrix is indeed symmetric. This one is 0 because there is no linking element between 1 and 3. Okay, so we construct the stiffness matrix, and it's now easy to determine the resonance frequencies and the modal shapes using MATLAB. So with MATLAB, as I said, it's quite easy to compute. You construct your mass matrix, your stiffness matrix, you compute the matrix A. It's the inverse of M times K, and then you can compute the eigen eigenvalues and eigenvectors, and to obtain the eigenfrequency, well, you should take the square root of the eigenvalues. Okay, so the result of the computation is that there are, as expected, 3 natural frequencies, but you see that the first one is indeed equal to 0. That's because this system is unrestrained, right? And you can have a look at the modal matrix. So here you see V1, V2 and V3. They are unit vectors, okay, and you see that they are perpendicular to each other because this matrix A is equal to M inverse K is indeed symmetric, right? And it's important to understand the interpretation of that. Well, for this resonance frequency, you see that x1, x2 and x3, they move in the same fashion. Okay, so it will not have any flexible deformation. Okay, in the spring will neither be expanded nor is it being compressed. Okay, this is the rigid body mode. If we're looking at the other modes here, for instance, for the second natural frequency, we see here that for this mode x2 will not move, and if x1 will move in one direction, well, x3 will go in the other direction. So here you see things represented graphically. So here you have the steady state, okay, and here you have the modes. Well, the first mode is associated with the first natural frequency 0. This is associated with the second natural frequency, and this is associated with the third natural frequency. And indeed, for this first natural frequency, because the system is unrestrained, we see that it's 0, and that it's a movement where the 3 masses are moving in phase. Okay, so you see that there is no strain on this spring or no strain on this spring. Whereas for the other 2 modes, and the first one, the next one is related to the second natural frequency, you see that the first mass is moving in this direction, the second mass does not move, and the other one is turning back. So here indeed you have compression. Okay, and for the third mode you have compression over here and the spring is stretched over here. Okay, so this is really the rigid body mode. So what is the movement of the original system? Okay, well, it's a linear combination of these 3 movements. Okay, you remember that the solution of our original problem will be v times x.